Hi, I'm Lindsay.
And hi, I'm Maggie, and we did our project on the volumes of stacked spheroids. So, our main objective question was how many balls can we fit into the cabin?
So, the first part of this question, obviously, is to find the volume of the cabin. Now, we had some rules that we set for ourselves when doing this. We decided that all disposable furniture would not be subtracted from the total volume of the cabin, but that permanent fixtures like the fireplace or kitchen cabinets would be subtracted from the total cabin volume. And so, as a final number, we got 1,246,788.208 feet cubed.
So, the types of balls that we used in this experiment or data collection were basketballs, baseballs, golf balls, soccer balls, and then we also used a football and a rugby ball. So, the first four are just typical spheres. So, their volumes were calculated using a formula that is 4/3 times pi times their radius cubed. And then we had the football and the rugby ball, which were not spheres.
So, for the football and the rugby ball, obviously, because they are not spheres, we needed to use a different equation. Now, the equation that we used was the volume equals 4/3 times pi times a squared times c. And a squared and c are obviously different variables than we're using the other equation. And a refers to the length from center of the long axis, and c refers to the length from center of the short axis of the football or the rugby ball. And when we plugged these numbers in, obviously we got the numbers that you see on the board right now.
So we decided to calculate the amount of balls that can fit into the cabin in two different ways. The original way that we used was kind of the image that you see in the top left right now, where we only took into account the volumes of the balls, and so you could see them as taking a cubic shape or see them as just kind of being a liter volume in liters in fluids, because it's just kind of taking in that amount of space. It's taking up that amount of space without having any extra air or unused space in between. Whereas the second amount of balls that can fit takes into account that space that ends up in between the balls when they are blown up and they're stacked like they're in boxes, because there ends up being space in the corners of those boxes, which all ends up adding up to around like the size of the ball when you're using the spheres. Because so when you see the one volume of the ball in the first table, you end up actually almost doubling it for the first four balls when you go into the second column, because of that extra space that is added around it. Therefore, then having the amount of balls that you can fit in the space. Whereas the football and the rugby ball, they don't end up having that much extra air around them when you put them into rectangular prism boxes as opposed to cubes. So you didn't lose quite as many when you included them in the boxes, as opposed to having them just be cubic and not including that space in the volume.
So now we move on to analysis, where we started with calculating the percentage of total volume that was used when the balls were their actual shape and sort of stored within boxes. And as you can see, for the first four, the spheroids, for the spheres, it was pretty consistent. It was around 52% for all of them, and that's because they all are essentially the same shape. But for the football and the rugby ball, the percentage of used space is quite different. It's much higher. For the football, it's around 90%, and for the rugby ball, it's around 80%, and that's because they are not perfect spheres. They are spheroids, and so the space around each individual football or rugby ball is less than that of the basketball or the soccer ball or the baseball or the golf ball.
So why does this matter? It shows the ratio between the volumes of the different 3D objects and the space that they take up around them when they're put into boxes or when they're stacked squarely, like you see in this image here at the bottom. The spherical balls take up around, like, the average was 52.36, sort of, with the one exception of the significant figure thing with the golf ball. But then when you move down to the spheroids with the football and the rugby ball, it's helpful to look at the percentages and see how efficiently they use their space, for something like a real life example.
So one real life example that we came up with was if you packed a mail truck. Now, traditionally, when you pack a package, you put them in a square box. And so if you packed a mail truck full of spheres, then you're going to have a lot of wasted space. If you stack them the way that we did, it's, about 48% of the space is going to be wasted around those balls. And so maybe in the future there will be a more efficient way of packaging spheres, still in a way that they will be supported and be stackable, but in a way that will take up space much more efficiently within the truck. But for spheroids like the football and the rugby ball, obviously there is a lot less wasted space within the mail truck. So I hope you guys enjoyed our project. I hope you learned a little bit, even if it wasn't what you were expecting to learn today. But thanks for listening.